All right, so let's go ahead and let's review for the quiz tomorrow, or for Wednesday, I should say. So this is the practice questions I'm going to be going through, and I posted this in the D2L for week 11. It's the last one here, PQ1, practice quiz 1. So we're going to be going through that. All right, so let's take a look at the first question. Binomial distribution. A bakery produces cookies, and historically 80% of the cookies pass a quality test. A quality inspector checks 15 cookies from the batch. Part A, what is the probability that exactly 12 of the 15 cookies pass the quality test? So this is a binomial distribution here. So we got to identify the binomial distribution factors, which are n and p and x. So in this case, n is a total number, which is 15. P is 0.8 and x is 12. So n is 15, p is 0.8, and x is 12. Okay, so it's exactly 12. So that means we want exactly 12. We want to find the probability that x is equal to exactly 12. So we can use our binomial distribution calculator here. And if you click in the D2L, you just got to click on binomial distribution. And you can put in your numbers, 15, 0.8, and 12. Make sure it's equal to. And it tells us it's 0.25. So the answer is 0.25 for that one. That's 1A. Let's take a look at 1B. 1B says, what is the probability that at least 13 cookies pass the quality test? So everything's going to stay the same. N is 15. P is 0.8. But now x is equal to 13. And we want to find the probability of at least 13. So that would be 13 or more. So x is greater than or equal to 13. So we go back to our calculator. And now we got 13 for x. These two stay the same, but we want greater than or equal to. So that would be 13, 14, or 15. So right here is what we're looking for. And that's 0.398, which we'll write as 0.398. C. What is the expected number of cookies that pass the quality test in this sample? So a bakery produces cookies, 80% of the cookies pass the quality test. At least a quality inspector checks 15 cookies for the batch. Okay, so that's just asking us for the average, right? So 1C is just asking us for the average, which actually we could use, well, we should probably use the mu symbol, which is just n times p. So in this case, n is 15, p is 0.8. So you just do 15 times 0.8. So I'll grab a calculator here. 15 times 0.8, we get 12. So we would expect to see 12 cookies pass the test. All right, so that's question 1. See, my camera turned off here, but I think you can still see my screen. So that's what really matters, I guess. So let's take a look at question 2, probability distribution expected value. So it says a game involves rolling a fair-sided dice. If a player rolls a 1 or 2, they win $5. If they roll a 3 or a 4, they win $10. If they roll a 5 or a 6, they win $15. Construct the probability distribution for the winnings. What is the expected value of winning? Okay, so that one is expected value problem. So for our probability distribution, we have x and p of x. And we can win $5, win $10, or win $15. There's 2 rolls of the die where we win $5. So that's 2 out of 6 or 1/3. Same thing for the $10 and same thing for the $15. So then when I calculate the, well, this would be my answer for part A, I should say. So that's my answer for part A. I'm going to actually erase the extra column there. We don't need that. So the expected value, which you could write as EX, or we're just essentially finding the mean of this, would be, so the formula for expected values, you take each X times each P of X, and then you add up the results, right? That means to sum up the results. So you take 5 times 0.3 repeating, 1/3 is 0.3 repeating, plus 10 times 0.3 repeating, plus 15 times 0.3 repeating. And if I go to my calculator, 5 times 0.3333 is 1.6. 10 times 0.333 would be 3.3. 15 times 1/3 would be 5. So adding up the results here, 1.6 plus 3.6 would be 3 plus 1 is 4. 5 would be $10. So we would expect to win $10 by playing this game. Would be the expected value. So this is 2A and that's 2B. Now, in this case, there were no negatives because we could only win, right? All right. Still connected here. Let's take a look at number 3, standard normal distribution. Let Z be, that should just be 1Z, by the way, a standard normal random variable with a mean of 0, standard deviation of 1. What is the probability that Z is less than negative 1.2? So 3A, probability that Z is less than negative 1.2. So what we do here is we go to our calculator, and we have a backup one here. We have a normal distribution calculator. So click on that. Mean of 0, standard deviation of 1. And in this case, that's a standard normal, so make sure the mean is set at 0, standard deviation is set at 1. In this case, we want it to be less than negative 1.2. So I'm going to put negative 1.2 in there. We want it to be less than that, so that would be that one. And we get 0.115. Remember, I do like it when you draw a picture of the situation. So in this case, the mean is 0, so standard deviation of negative 1.2. That would be my Z-score. We're going to the left of it as well. 3B. Find the Z-score that corresponds to the 80th percentile. Okay. So the 80th percentile would be here somewhere, such that it's greater than 80%, right? So we want that to be 0.8. So what would the Z-score be here that would give us 0.8? Well, we can go to our calculator. So we don't know that, but now we know this is 0.8. So 0.8 gets entered in, and that would be the Z-score that gives that 0.8, so 0.84. Z would equal 0.84. C. Find the probability that Z is between negative 1 and 2. All right, so if we draw a picture of this, negative 1 and 2, 2 is going to be greater than the mean, negative 1 is less than the mean. We want to find the area between, right? So the probability that Z is between negative 1 and 2. So if we go to our calculator here, the way that we actually do this is we calculate the probability that Z is less than 2, should be this one. Just go back, make sure, because I heard a noise there. Stay on the call, there we go. Okay, so calculate the probability that Z is less than 2 minus the probability that Z is less than negative 1, and that will give me the area between. So that would be 0.98. We're going to round that to 0.98. Minus probability that Z is less than negative 1. would be 0.16. So 0.98 minus 0.16 would be 0.88, 0.82 for that one. Number 4, normal distribution problem. The heights of population of adult men are normally distributed with a mean of 70, standard deviation of 3. What is the probability that a randomly selected man is taller than 74 inches? Okay. So for 4, the mean is 70. Standard deviation is 3. For 4A, it says our value of X is 74 inches. Should use the inch symbol for that. So if we do that, there's our bell curve. Mean is 70, so 74 is going to be over here, and we want to calculate the probability that they're taller than 74. So go to our normal distribution calculator. We do have to change our mean to 70, standard deviation to 3. Our X value is 74. We want it to be greater than that, so that's 0.09. Part B. What is the percentage of men that are between 67 and 73 inches tall? So remember, I want you to draw the picture. So 73 is going to be on this side. 67 is going to be on this side. So we're looking for that. Now, that's within 1, right? So we can use the empirical rule. We know the answer is going to be 68%. But let's take a look at it and see what the calculator says. So this stays the same. So using the calculator, we have to do the probability that X is less than 73 minus the probability that X is less than 67. So that's 84%, 0.84, minus the probability that X is less than 67. 0.16. Which is 0.74, which is 0.68. So it does work out. Perfect. All right, let's take a look at 4C. If the shortest 5% of men are eligible for a certain study, what is the maximum height of men eligible for the study? So the shortest 5% on the bell curve, that's going to be over here. We want that to be 0.05. Now we actually know based on the empirical rule that actually we don't, never mind. We can't use the empirical rule. So we can go back to our chart. And in this case, we want to find X. So I'm going to put, this is going to be 0.05. And that's going to give me that shortest 5%, which is going to be 65 inches. So that would be 65 inches would be where the marker is there for our answer. All right, last one here, question 5. The central limit theorem. A bottling company produces bottles that have an average capacity of 500 milliliters, standard deviation of 10. Part A, if a sample of 25 bottles is selected, what is the probability that the sample mean capacity will be between 495 and 505? So n equals 25. So remember, the mean of the samples is the same as our mean, so that's 500. The standard deviation of the samples equals standard deviation divided by the square root of n. So it's 10 divided by the square root of 25. And that's going to be 10 divided by 5, which is 2. So now, when we go to the bell curve, we want it to be between 495 and 505. Well, this is actually the empirical rule. because, or actually it's not, again, sorry, it's not, because I was thinking standard deviation was 5, but it's 2, never mind. So we're looking for between 495 and 505. So we got to use the calculator for that. So we're going to enter 502, and then we want to find the probability that X is between 495 and 505, which is going to be the probability that X is less than 505 minus the probability that X is less than 495. So 500 and 2 and 505. So that's 0.99. And the probability X is less than 495. 0.006. So we can round that down if we want. I rounded this, so 0.99 minus 0.006 is 0.984. That's part A. All right, 5B. How would the probability change if the sample size was increased to 100 bottles? So with that one, if we change the sample size to 100 bottles, right, we know our mean is 500, standard deviation is 10. So our mean of X is equal to 500. Our standard deviation of the sample is equal to 10 divided by now the square root of 100, which makes it 1. So now in the bell curve, it's going to stay the same between 495 to 505. So same idea as before. We go back, we're doing this probability here. We're doing this right here. But instead, we're using our new information. So let's put that into the calculator. So now our standard deviation changes to 1. We have 505, which they're saying it's 100%. If we put 495 in there, they're saying it's 0. So if we do that, the probability that X is between 495 and 505 is 100%. All right. The last question, explain how the central limit theorem applies to this situation. That's just based on the fact that when you take this, the average of the samples of a distribution, that comes to a normal distribution. So the central limit theorem allows you to take any distribution of any shape, even if it's not normal. And if you take sample sizes, you take the average of those sample sizes, then you can use the central limit theorem. All right, hope that helps. Let me know if you have any questions.